What is gravity? So according to us, when we are looking at gravity, gravity is going to be the force which is pulling all the objects towards the Earth's surface. That's what's the thing we used to think of. Let us keep this thought aside and then let us look into what is actually the gravity is. When we are looking at gravity, if we are having any of the object on the Earth's surface like a person or a tree, all of them are being pulled towards the Earth's surface. But when the pulling is happen, that is the force which is given by the Earth on the other objects. It's because Earth is having a huge mass associated with that. Whenever we are having two different masses, the masses will always try to attract each other. That is, the person over here will try to pull the apple with a particular amount of attractive force. Similar way, the apple will also try to attract the person with a particular amount of attractive force, which is actually termed as gravity. But more the masses, more the forces. So as we all are on the Earth's surface and Earth is having a higher force, we do call the force of attraction by the Earth as the gravity. That is the attractive force between two objects with the non-zero mass separated by a distance is gravitational force. Whenever we are looking at the Earth and the force given by the Earth, it's similar to an example like this. Whenever the class teacher is in a class and the student wants to talk, the students will be talking but the voice of them won't be audible, but the class teacher voice will be audible. Similar way, Earth is like a class teacher who is having the higher authority compared to the students over there. That is why whenever we are on the Earth's surface, we can't able to feel the force of attraction between ourselves, but we do feel only the force of attraction of the Earth. This is the same reason why can't we able to see the gravitational force of attraction between any of the two objects which is going to be on the Earth's surface. So when it comes for the question about an apple falling towards the earth, either the apple is moving towards the earth or the earth is moving towards the apple. The answer for this, same way when two persons are not attracting, similar way when two swords are not colliding. The reason is the distance between them as well as the mass of them. Let us look at the reasons in this video. 8. Gravitation. Hope you all know this person, Isaac Newton. When we are hearing about his name, the first and foremost thing which strikes in our mind is nothing but the apple. That is the apple which struck his head, and then because of that he found about gravity. Every one of us know about only the part of the story how the gravitational force has been first found by Isaac Newton. We all thinking that apple has fallen on his head. Why the apple have fallen on his head? Because of that only he found the gravitational force. But actually the reason behind how he found gravitation is nothing but he was looking at the apple which fallen on his head, as well as he was looking bit above where we have a white color apple there, that is our moon, right? So the moon, what is over there above the earth for a very long time, it's not falling down even though it's having a higher mass, but the apple which is of a small mass could able to come down, or that is it's getting falling down, right? So what is the reason behind it is the thing what he was thinking. So if you are having masses, mass could able to get attracted by the earth, but there is one more factor is there which is not allowing that mass to come towards the earth as well. So by combining these two factors only, he has given about the gravitational force law. Exactly about the same thing only we are going to discuss with today's session. The two factors which says about the gravitational force between any two of the masses we are going to have is nothing but the mass of the object what we are going to have, as well as the distance between the two objects what we are going to have. So in the case of apple as well as in the case of moon, these are the factors which are going to be the base of this gravitational law, where we are looking at the mass of the apple as well as mass of the moon. Both of them are having masses, but the mass of the apple is very less, the mass of the moon is very huge. And we have to compare these masses with the mass of the earth. So the mass of the earth is going to be very big. Closer to that bigger mass, we have the apple over there, and we have the bigger mass, equivalent to the mass of that, we have the moon over there. So when the moon is trying to attract the earth as well as the earth is trying to attract the moon, both of them are having a particular amount of distance between them, which balances the force of attraction among themselves. But when it comes for the case of the apple is going to have a higher amount of attractive force. This is because the apple is closer to the earth as well as the earth is so bigger compared to the size of the apple. This is where the attractive force lacks between two of them, or it's going to be very high between them. So every particle which is considered to be a matter is going to attract another matter which is having a mass. That attractive force is going to be directly proportional to the masses what the objects are having. As the mass of the earth as well as the mass of the moon, both of them are high, the force of attraction between them is also high. When it comes for the apple and the earth, the distance is less and the size of the earth is more, so that it is easily attracting the apple towards it. So when experimentally it has been done, the distance is going to be inversely proportional to the force of attraction between them, and the experiment result shows that the square of the distance between them is going to be inversely proportional to the force of attraction between the two massive objects what we have. And it is the same thing which is going to be directly proportional to the product of the masses of the objects what we are going to have. So when we are trying to write it as an equation, F is going to be directly proportional to m over r square we are going to have, where the proportionality constant should be removed in physics. Always the proportionality will be taken out and then there is a constant is being written over there, means there will be a constant. So that constant is nothing but capital G over here, which is called as the universal gravitational constant. So when we are taking the two masses over here, the first mass is going to be taken as m1, the second mass is going to be taken as m2. The force of attraction given by the mass m1 on m2 is going to be given by F21, as well as the force of attraction given by the m2 on m1 is going to be F12 vector what we are going to have. The distance between the two masses is going to be r if you are taking. Then according to the Newton's law of gravitation, the statement is going to tell us that the force of attraction between them is directly proportional to the product of their masses. That means that F is proportional to m1 m2 over, and F is going to be inversely proportional to square of the distance between them. Then it is going to be inversely proportional to r square what we are going to have over here. So to take off the proportionality, what we have to add here is a constant. So the constant is going to be the gravitational constant capital G what we have. So the value of the universal gravitational constant is 6.67 into 10 power minus 11 Newton meter square per kilogram. Now there must be a doubt that how come we have a unit for a constant here, right? So when we are looking at the unit for the constant over here, the unit of the force is going to be Newton. Then the masses we are having over here, so we will be having that as kilogram square. Then for the distance we are having meter square. When we are taking all these terms to the other side of this equation, then automatically we are going to get the unit for the G what we have over here. So G is going to be constant throughout the universe, and G does not depend on the medium between the two masses m1 and m2 what we consider over here. So basically what is the difference between, see, we used to say the gravitational force of attraction of the earth is going to be small g, and the value of that is going to be 9.8, and always it remains constant, right? So if it is going to remain constant, then what about this capital G what we have? So basically the difference between them in that the first one is going to be G is the universal gravitational constant, but small g is going to be acceleration due to gravity. When we are coming for the value of them, the capital G is going to have the value of 6.67 into 10 power minus 11 Newton meter square per kg square. But when it's going to come for the value of the small g, that is going to be of 9.8 meter per second square. The value of this will remain constant throughout the universe, but this G value can vary place to place. For example, on the Earth's surface, the value of that is 9.8. When you are going for the Moon surface, the value of that is going to be 1 by 6th of the Earth's surface. Now let us explore the relation between capital G and the small g. If we are considering the mass of the Earth as capital M, and we are going to take an object which is having the mass of small m on the Earth's surface. The acceleration due to gravity on the Earth's surface is going to be small g, and the radius of the Earth is going to be taken as capital R. Then when we are looking at the figure, we will be getting something like this, where we are having the Earth, mass is capital M, the small mass, a ball-like structure which I consider on the Earth's surface is going to be of small m. Then the distance between them from the center of the Earth is going to be given as capital R, what we have over here, right? So when we are taking such a case, the amount of force felt by the mass on the Earth's surface will be given by the weight of the object, which is mg. Then according to universal law of gravitation, the force of attraction given by the Earth, or between these two, is going to be given by G capital M small m. That is the product of the two masses over the distance between them. The distance is going to be the radius of the Earth, which is r square, where this m and m is getting cancelled, because here the small m is the mass of the object on the Earth's surface. This is also the mass of the object on the Earth's surface. So if we are cancelling both of them, the final relation for the gravitation is going to be small g is equal to capital G m divided by r square. When we are looking at the same relation, which is going to be for an object at a particular height above the Earth's surface, then also we are going to write the same thing. The weight of the object is going to be written as mgh, where the gravitational force of attraction between them will be given by gmm divided by r plus h the whole square. When you are cancelling this 2 m's on this side, then the relationship is going to be given by gh is equal to gm over r plus h the whole square. When we are going to look at that one, by dividing the relationship between g and the small g, that is what we consider as the equation 1 as well as equation 2. When we are dividing them, the value of the new acceleration due to gravity at that particular height h is going to be given by g into r over r plus h the whole square, where g is independent of the mass what we are considering. Projection of a satellite. See, whenever an object wants to move away from the Earth, it has to move towards the upward direction. Whenever it tries to move towards the upward direction, the Earth gravitational force will try to pull it down, right? So why it is necessary to have at least two stages of the rocket to launch a satellite is nothing but we should make the object to move out from the Earth gravitational force of attraction. So a rocket with at least two stages is required to launch the satellite, because the first stage used to carry the satellite up to the desired height. By burning that part, it will be helping the rocket to reach that particular height. In the second stage, the rocket is going to be turned horizontally at 90 degree, and the satellite is fired with the proper horizontal velocity to perform a circular motion around the Earth, right? When the satellite is going to be projected, the satellite must be reaching the second stage, where the satellite is going to be projected in a horizontal mode with a particular velocity, so that velocity helps that to revolve around the Earth's surface in a circular path. So the velocity with which the satellite is going to revolve around the Earth is called as the orbital velocity or the critical velocity of the satellite what we are having. When we are coming for the terms called as Kepler's laws of motion, the Kepler's laws of motion helps the objects to revolve around the Earth's surface. Basically, who's Kepler when he born, when he died is the one what you're seeing here. He was born on December 27, 1571, and then he died on November 15, 1630. He is a German, and basically he is a mathematician as well as astronomer as well as astrologer. When we are going for the Newton's first law of motion, what is the Newton's law of motion telling us is nothing but whenever there is an object is going to be in motion, it requires a force, right? Similar way, if the planetary system, that is what is the solar system we have, those planets are in motion means they should also have a force between them. That was the one which is being proposed by the first law of Kepler, which is called as law of orbits. So every planet revolves in an elliptical orbit around the sun, with the sun situated at one focus of the ellipse what we are having. So the foci what you are going to take, the area which is near to the foci is going to be taken as perihelion, and which is away from that is going to be called as aphelion. And along as its elliptical path in which the satellites are going to revolve around or the planets are going to revolve, we do have that as an elliptical shape, so it's having a major axis as well as minor axis. So whenever this revolution is going to happen, always the masses are going to be in, that is the star is going to be at any one of the foci of that only. When we are coming for the Newton's second law of motion, it tells us about the law of equal areas. So if you're going to look at the area over here, see when it's going to be closer to the sun, the force of attraction is going to be more. So the area swept, that is the area crossed by the planet from one point to another point, will be very high. As it's closer, the force of attraction is more. Same way, when I'm going to take a point which is farther away from it, the force of attraction between the sun and the earth or any planet is going to be less, according to law of gravitation. Distance is more, so attractive force is less, so it will be moving slowly. But over here distance is less, so attractive force is more, so it will be moving faster. Because of this, we will be able to see that here small area covered, here very huge area covered. But the distance between them also matters. So because of that, whenever in a particular given time, if you're going to look at the areas swept by the planets around the sun, will always remain same. That is what is the second law of Kepler tells us about. Then when we are looking at the Kepler's law as the third law over here, the time taken by the planet to revolve around the sun is going to be proportional to the distance between them, which is taken as the time square is going to be directly proportional to r cube. Once again, how the square and cube came over here is nothing but continuous technical observation for a long time. Just change the statement that time is directly proportional to the distance into time square is directly proportional to r cube. So what does this law says is nothing but the square of period of revolution of a planet around the sun is directly proportional to the cube of the semi-major axis of the elliptical orbit. So according to this law, when a planet is closest to the sun, its speed is maximum, and farthest from the sun, its speed is minimum. Let us see the calculation of critical velocity when we are trying to project a satellite. So over here we have a mass of the earth which is capital M, which is having the radius of capital R, and the satellite is going to be at the overall distance from the center of the earth as small r. But on the earth surface, from the earth surface, the satellite is going to be projected at a height of h, what we have over here. As the satellite wants to revolve around the earth surface, we have to project it with the horizontal velocity called as critical velocity Vc, or orbital velocity Vc. So let us look into it now. When we are looking at an object which is going to revolve around the particular object in a circular path, it should have a centripetal force, where the centripetal force formula we know that mv squared over r. But over here the v what we are going to consider is the critical velocity what we have. So I have written that as vc square, and the centripetal force is going to be balanced by the amount of gravitational force of attraction between the earth and the satellite. So that is going to be given by, according to Newton's law of gravitation, as gmm over r square. Here the m is representing the mass of the satellite, so both of them are getting cancelled on both the sides. which is giving us VC square is equal to GM over R square. So VC is equal to root of GM divided by R. So this EM we should not write over here. Critical velocity of the satellite has been found as VC is equal to root of GM divided by R, where the factors what we have over here is nothing but the mass of the planet, height at which the satellite has been situated, as well as the radius of the planet what we are going to have. So basically the critical velocity of the satellite is going to depend upon the mass what we have over there only. So when we are trying to look at the critical velocity of the satellite about a height, then the g value should also get changed. So according to that, if you are trying to write the g value, gh is going to be given by gm over r plus h the whole square, which is a relation we found for a satellite which is at a particular height before some time. So GM is equal to GH into R plus H the whole square is the final result what we are getting. If we are substituting this value for the GM in the VC equation, then finally we are getting that as VC is equal to root of GH into R plus H. So this is the final equation